are going to perform some problems, and before that let me finish some 2 or 3 theory parts to the problem. Okay friends, time we were discussing about the closed loop system. In the closed loop system, see, now you are familiar with this op-amp symbol, right? Here we are taking V0. These are two terminals, namely V1 and V2. V1 and V2. This is inverting terminal, this is non-inverting terminal. If you are taking feedback from output and connecting with negative terminal, let's take the feedback element beta. It's called the negative feedback. Negative feedback. Okay, and in the last class we have seen why negative feedback is important than positive feedback. Okay, we have seen one thing there, that in the negative feedback the gain of the system is reduces, but overall system efficiency increases. Okay, why increases? If you will connect the negative feedback into the circuit, it will autocorrect itself, but apart from this you will get some extra benefits of it. In the negative feedback, it stabilizes the gain. The fluctuation in gain or changes in gain will be now stable. Increases the bandwidth and changes. If bandwidth will increase, so definitely it's good for us. Okay, it can take large amount of signals. The input and output resistances, and also increase the bandwidth and changes the input and output resistances. Other benefits are reduced distortion. If distortion will be reduced, then it will be benefit to us. And reduced offset voltage, output offset voltage. Offset means error. If you are getting output offset voltage, means you are getting unnecessarily or undesirable output. So negative feedback reduced to that one also. It also reduces the effect of temperature and supply voltage variation on the output of an op-amp circuit. Okay. Now if I'll compare this with the control system block diagram kind of thing, this is your gain of the system, perfectly fine. Here you are taking output, let's take it CS. Okay, at this stage you are applying input, let's take it XS, but what you are doing, you are sampling the feedback from the output. Let's take the feedback circuit element beta. You are connecting, mixing over here at the input stage, and this is the minus because this is the negative feedback. So this is the block diagram or block diagram representation of the op-amp circuit. So here if someone will ask what is the transfer function of this block, so the transfer function is nothing but the Laplace transform of output divided by input, and all initial conditions are 0. So it will be A1 plus beta A if you remember this. This is the control system. Okay, this is transfer function. Is it okay? So you can see over here, if A is very large, so for the op-amp circuit A is very high, near to infinity. Okay, so at A equal to very high or infinity, let's take its ideally CS is equal to XS. Means whatever you are applying at the input, you are getting at the output without distortion. Okay, so this is the application of the negative negative feedback. We'll see it later. So the connection, if you are connecting the feedback or taking feedback from the output, we have 4 types of feedback connections. These connections are classified according to whether the voltage or current is feedback to the input in series or in parallel. Okay friends, the first one is given the voltage series feedback. I can call it series also. Series feedback. Okay, earlier I told you about input and output stage or input and output resistances for various these stages: voltage control, voltage source, current control, for various amplifications. So if you have voltage control, if you have current control, or either you have voltage source or you can have current source. If you have voltage source at the input stage, you will be having R infinity. If you have current source at input stage, your R will be 0. If you have, let me take pen. If you have voltage source at the output, R naught should be 0. If you have current source at the output, R naught will be infinity, like this. So at the input stage, if voltage is there, so R will be infinity. At the output stage, if current will be there, then R will be infinity. Is it okay? So please remember this thing. So when anything is going to series means obviously resistance become high, because in the series circuit, you have seen in the series circuit, if you have 2 and 2, they are connected in series, means they are going to adding, see 4, it will be 4 ohm. So in series circuit, always resistance increases. Okay, it will never decrease, always increases. So based on output and input, we are having 4 types of feedback, and 4 types feedback are, let me erase some part. The first one is voltage series. If I am writing it series and series, so this represents input, this represents output. But if I am writing by name like voltage series, in this case, the first one is representing output and second one is representing series. Okay, if I am writing like this, taking name over here, voltage. So the first step is related to output and second stage is related to input always. Now we'll see what is the series and what is the shunt and what are these 4. Okay. So let's come like this. First we have seen the voltage series feedback. Voltage series feedback. See, what I'm telling is, please focus over here. You have voltage series. This belongs to output and this belongs to input. So input is series means at input level you have voltage control. We have seen in the formula. Just now we have seen in the formula. If R is infinity, so voltage control. This is current control. If R is 0, voltage source. If R is infinity, current source. So infinity means resistance is going to increase, means I can give the name series, and 0 means shunt. So shunt means 0, series means infinity, or in other words I can say series means resistance is going to increase, shunt means resistance is going to decrease. Okay. So at the output we have voltage. Output voltage means voltage source, means R is 0. R is minimum or very low means shunt. So at the output stage, see, again I'm telling you, don't be confused yourself. You have written voltage series. What I'm telling is, this is output stage. At the output stage you have to take the voltage. So at the output stage we have sources only. At the input stage we are having control sources. So voltage source. Voltage source R at the output is 0. Just I showed you, right? 0 means you have to call it shunt or parallel. In the case of parallel only, your resistance is going to decrease. Is it okay? If 2 elements are connected parallelly, 2 and 2, so resultant will be 1. So this 1 is, less than this 2 and 2. Is it okay, friends? So now output stage will be shunted. See, this is the output. This is the shunt. I shunted output. Shunted out means at two terminals of output, I'm taking input and feeding this input to the feedback. Is it okay? This is parallel kind of thing. Two terminals A and B are given. Just I'm taking like this. So these two terminals are common for this also and common for this also. These two terminals are common for this box also and this box also. So they are connected in the parallel combination. So parallel means a shunt. So this voltage is clear now. Voltage series, another name is shunt series. The another name of this is shunt series. Okay. Now at the input stage you need series. So you have to connect these two boxes in series. So two box how to connect in series? In this way. In this way you have to connect. See, if two boxes you want to connect in series means you have to connect in this way. Is it okay? And if you are completing the circuit, so it will be like finally this. Okay. So similarly, you can understand all this. Voltage shunt means at the output stage you have shunt, and this is the input stage already defined in the form of this shunt. Shunt or parallel. From the output also I'm taking parallel. At the input also I'm feeding this in parallel way. So this is voltage shunt. Now what is current series? Current at the output is always infinity resistance. Infinity means series. So this is the series. So at the output stage also I'm taking series. You can see over here. These two boxes are connected at the output terminal in series connection. At the input terminal also in series connection. This is the current shunt. At the output you have series. At the input you have shunt. Is it okay? Now this one is the very important concepts, or I can say this is the building, this concept is the building block of all your problems we are going to do. So again I'm drawing the op-amp circuit, so it will be pretty clear to you what is the virtual ground. See friends, you have two terminals. Two terminals, let's take it V1 and V2. This is plus, or this is minus, or this is plus. You are taking over here some feedback circuit also. Let's take it R. You are taking output V0 over here. Now what virtual ground says, or virtual ground concept says, tell me one thing. What is the gain of op-amp? Always in the range of mega or giga. Okay. So this is 10 to the power 6 I'm taking only. Okay friends. Now we apply the power supply to the op-amp also, like plus 12 to minus 12. So this is the limit, or we are going to limit the op-amp, that op-amp can't work beyond this. Up to 12 volt you can use it, and beyond 12, yeah, and beyond 12 there is a distortion or clipping into the circuit. So tell me one thing, at the input stage V1 and minus V2, the difference of these two are going to multiply with 10 to the power 6, and you are getting some V0. Is it okay? So see how small this signal is. The range of this signal is itself 12 by 10 to the power 6. The V1 can't exceed this point. 2 points range we have, 12 by 10 to the power 6, and 10 to the power 6 is the gain. Whatever you are going to apply over here, it will be multiplied by 10 to the power 6. The highest max is 12 only. So it can't go beyond 12. You can't apply over here 1 volt and over here 3 volt. If you apply 3 volt over here, 1 volt over here, so difference is 2, will be multiplied with 10 to the power 6. At the output you are getting 2000 kilovolt. So this is not like that. Op-amp is the circuit used to work on 5 to 10 volt only. This is the electronic circuit. Okay. So what I'm going to tell you, that the input we chosen in such a way that the distortion should not come in at the output stage, or clipping should not come at the output stage. So V1 you will choose so that V1 by 10 to the power 6 should be, your input is not greater than this. The max input you can take is this only, because your V1 is going to multiply with 10 to the power 6. So 10 to the power 6 and 10 to the power 6 will cancel out and you will get at the output V1 minus V2. I hope you are getting what I'm saying. So your two inputs for op-amp are very small. Okay. Wait a minute. So for op-amp, the two inputs are very small, V1 and V2. V1 and V2. This is 10 to the power 6. Suppose this is the supply 10 plus 10 and minus 10. So your V1 will be in the range of 10 to the power 10 to the power 6 means 0.00001 10 to the power minus 5. This is the V1. And if I'll talk about V2, you are applying something and it will be again 0, 0 and 2 like this. So they are both are nearly equal or not? V1 is nearly equal to V2. If we are talking about the very small quantities, they are nearly equal. So what we are considering is by virtual ground concept, whatever voltage given at V2, the same voltage will be reflected at this point also. This is the virtual ground concept. Virtual ground concept means this voltage is not exactly over here, but equal to or approximate value of this voltage is presented over point A. So I assume that V1 is equal to V2, or in other words I can say the non-inverting terminal voltage is equal to the inverting voltage terminal. Okay. So some people will take this concept in wrong way. What they will say? They'll say like they are shorted. If they are shorted, then only this voltage become this voltage. Okay. I am not saying this is the ground concept. I'm saying this is virtual ground concept, imaginary kind of thing. Okay. And why they are equal? Because they are very low. They are equal because of very low, not they are short circuited, because here the infinity resistance is there. You know very well, for the op-amp the input resistance is infinity, means they are opened inside, they are not shorted, but still the V2 is equal to V1 because of these small values. This concept is called the virtual ground concept. Is it okay, friends? So voltage equation V0 is AD VD, perfectly fine. VD is V0 by AD, no doubt at all. VD is the difference. Okay. Since AD is very large, so VD is tends to 0, the difference I'm talking about. VD is difference over here. So VD is nearly 0 or not, tell me. Because difference is 0. If V1 is 0.00001. If V2 is 0.00015. If you will differentiate, if you will take difference of these two, it will be nearly 0 or not. Is it okay? So because what is the reason? The gain is very high. So in this case, ideally V1 equal to V2 it means. The difference V1 minus V2 is nearly 0. So V1 equal to V2. This is the virtual ground concept. This says that the voltage at non-inverting input terminal of an op-amp is approximately equal to that at the inverting input terminal, provided that AD is very large. Please try to understand the condition, foremost condition for virtual ground is AD should be very high. AD should be very high. This is the foremost condition for virtual ground concept. Okay. This concept is useful in the analysis of closed loop op-amp circuits. For example, ideal closed loop voltage again can be obtained by using this the results. So this is about virtual ground concept. Okay, based on this virtual ground concept, let me take some problems. So the question is, this is GATE 2003 question and 2 marks. And the circuit of the question is, so today we started the problem based on op-amp, right? Negative, this is the inverting terminal. Positive, this is the non-inverting terminal. And so whatever you will apply at the positive terminal, it will not inverted at the output stage. Here, this is 1K. Yes, correct, 1K. 1 milliampere, 1 milliampere. And 1 milliampere, and this is connected with 5 volt. Perfectly fine. Here It's 1.5k ohm connected over here. This is your question, and they are asking the op-amp and 1 milliampere current source in the circuit of figure are ideal. This and this both are ideal. The output of the op-amp is, this is the output. They are asking if both are ideal, what is the output? This is their questions. Now friends, we just discuss about the virtual ground concept. So virtual ground concept says, remember two things for virtual ground. The very first is your AD should be very high. This is the first condition. And second condition is there should be only negative feedback. In negative feedback, V1 equal to almost V2. Okay, so two conditions should be there. You have to check. Wait a minute. So two conditions you have to check. AD should be very high and the op-amp should be feedback by negative feedback. Okay friends. So the thing is, I'll start with that virtual ground concept. Here the voltage is 0. So definitely at this point also the voltage will be 0 because of the virtual ground concept. Once you know the voltage over here is 0, you can apply nodal analysis at this point A. I'll apply nodal analysis. It will be 0 minus here V0 divided by 1.5k. And into this branch 1 milliampere current is coming equal to 0. This is op-amp, and op-amp, see, op-amp does not take current. Input current for op-amp is 0. Is 0. Why? Because R is infinity. Whatever voltage you will apply, the current will be 0 for that. Current will be 0. So this is like this. So ultimately this is like this. So minus V0 equal to 1.5. So V0 equal to minus 1.5 volt. An option of minus 1.5 volt is also given over here. Okay. So this is the way to solve op-amp circuit. Is it okay to you? Let's take another problem. So friends, let's take another problem. This is GATE 2006 problem. And only 1 marks problem. Okay, the problem says, this is 5-second problem also. I think 5-second will be, see, this is VI given over here. The circuit I'm drawing, V0, obviously negative feedback, 10k, and this is R and this is grounded, this is plus, and he is asking if the value of the resistance R here in the following figure is increased by 50%, the value of this increased by 50%. Then the voltage gain of the amplifier shown in the figure will change by. Then the voltage gain, they're asking voltage gain, V0 by V in, changed by, options are given, 50%, B, 5%, C, minus 50%, and D, negligible. Negligible amount. Friends, tell me one thing. If you keep 10 ohm or 10k ohm or whatever ohm, is there any change over here? Ultimately, the voltage over here is 0. Why? Because this is directly connected to the ground and there is a no current in it. We know that op-amp, see, this is the op-amp. Op-amp does not take any current from the circuit. So current is 0, no voltage drop. Whatever the value of resistance will be at the positive terminal, at every time, whether it's R or 2R, 3R, the voltage will be 0. The same voltage will go over here. Now at any value of R, if you will calculate, the V0 by Vi will not change. It will not change ideally, but practically it will change with negligible amount, like 10 to the power minus 10 amount. Okay, so this is hardly 2-second question if you know about the concepts. Okay friends, I hope it's clear to you. Let's come to the next. So the problem is given. The problem is given that, let me draw the circuit. Op-amp, inverting terminal, non-inverting terminal, and this time the non-inverting terminal is not grounded. So 10K is given over here, negative feedback they are using, and it is 100K connected with output stage and V0 over here. And these two are connected with 1 volt battery. This is 1 volt battery. Is it okay friends? Now the question is, let me read it. Wait a minute. The question says the op-amp circuit shown in the figure, find out the output voltage V0. Find out the output voltage V0. And options are also given 11 volt and B equal to minus 10 volt, C equal to 9 volt and D equal to 1 volt. So friends, here also 1 volt, here also 1 volt. This is meaning by this. Is it okay? So 1 volt at positive terminal will come over here also. This voltage is also 1 volt. This is the virtual ground concept. If this is 1 volt, I can apply nodal analysis over here. This 1 minus 1 divided by 10K, minus 1 divided by 10K. There is no potential difference. Definitely current will be 0 over here. The current will be 0. Plus this 1 minus V0. 1 minus V0 divided by 100K equal to 0. So this is 0. 0 plus 1 minus V0 divided by 100K equal to 0. So ultimately 1 minus V0 equal to 0. And finally V0 equal to 1 volt. Is it okay? So this type of questions are there in this op-amp circuit. Very easy question. And 70% they're asking from op-amp only. Okay, let's take another problem. So problem is given like the op-amp circuit, output E0, negative feedback, minus, this is plus over here, connected to R1, further connected with R2, and R2 is grounded. Over here the voltage difference is E. Okay, and asking for, this is the given, this circuit is given. Pick up the correct relationship for the circuit shown in the figure. This is the circuit and options are given. We have to pick the correct relationship. E0 equal to E1. The question is, or B, E0 equal to R2 by R1 E1. C, I equal to E1 by R2 and D equal to E1 divided by R1. So 4 relationships are given over here. So this question, if this question will come, 80% will student mark directly E0 equal to E1, because this is the virtual ground concept. Whatever the voltage given over here will be over there also. So E0 equal to E1, clearly visible like this. Okay, so answer should be A. But this is not answer. This is wrong. Why wrong? I'm telling you. At the positive terminal, the voltage is not E only. It's given E1. Okay. Wait a minute. It's E1. So this is not E1 is not given with respect to ground. This is given with respect to this point. So whatever voltage we consider at any point in the circuit, it should be with respect to ground only. So if you want to consider the total voltage at positive terminal, it should be with respect to ground. But your E1 is with respect to this point also. In this circuit, the current I is given. So I need to calculate total voltage at this point, and that will be equal to E0. So this I current is coming. This is the open circuit. So definitely some voltage drop will be there across this, and the voltage drop will be R2 into I. Now if we will calculate total voltage here, so it will be E1 plus this. So total voltage is E1 plus R2I. E1 plus R2I, the direction is same. So this is the total voltage over here, and this voltage is equal to this voltage, and this is E0. E0 is directly with respect to ground only. Okay, so taken with respect to ground, not connected with ground. Okay, so whatever voltage is over here will be equal to the V minus. So this should be equal to E0. Is it okay to you? Now E0 minus E1 equal to R2I. Is this relation given over here? Wait a minute. So let's check over here. The relations are given in this way. Okay, so you need to find out whatever given in a given format. Okay, so how we will convert this into given format? So let's take it equation 1. We'll take it equation 1. And second equation will form by this only. I is given. I is what? This is E0. E0 minus this voltage. This voltage is minus R2I. R2I divided by R1. So here IR1 equal to E0 minus R2I. Two equations you have. Equation number 2. Now if you will take this E1 this side and R2 minus I this side, so E0 minus R2I will be equal to E1. Now you can replace this over here. So you are getting IR1 equal to E1. So your answer is I equal to E1 by R1. Do we have in options? Yes, we have in the option. So this is the correct answer. Okay friends. So once if you are sound in virtual ground concept, you can solve any problem related to op-amp. Okay. Let me take some more problems. This problem came in GATE 2011 and 2 marks problem. Okay. The problem is, this is 40. V0 over here connected with 8K like this, connected with 2K, grounded, X, op-amp. This is inverting, non-inverting is 6, and this is the base. This is the question given. This is X point connected with minus 2K. Everything is given. Options are also given. 24 volt. B is given 28 volt. C is given 30. And D is 32. Okay. Now the question is the value of V0. The series regulator shown below is, here is the V0, and they are asking the value of V0 only. Let me change the pen. They are asking the value of V0. Okay. So friends, virtual ground concept, whatever at the non-inverting terminal will same to the inverting terminal. So this voltage is 6. This voltage is definitely 6. Is it okay? If this voltage is 6, if you know this voltage 6, you can apply node analysis itself over here only. Current in the op-amp will always 0. So apply nodal analysis as point A. Let's take it point A. Nodal analysis. Nodal analysis at point A. Point A. 6 minus V0 divided by 8K. Okay. Plus 6 minus 0 divided by 2K equal to 0. So you can take LCM. 8K 6 minus V0 plus 24 equal to 0. So V0 equal to 30 volt. Hardly 30-second problem. 2 marks problem. And the option is C, 30. Is it okay to you? Let's come to the next concept, and concept is bandwidth. The bandwidth of op-amp circuit. Okay. The frequency at which gain equals 1 is known as the unity gain bandwidth. Unity gain bandwidth. Because earlier we have seen gain and bandwidth is constant. Okay, and unity gain is, what is the bandwidth? If your gain is unity, then bandwidth gain product is bandwidth itself. Okay, so the frequency at which gain equals 1 is known as the unity gain bandwidth. It is the maximum frequency the op-amp can be used for. So bandwidth is the maximum frequency at which the op-amp is at max work. Okay. Furthermore, the gain bandwidth product obtained from the open loop gain versus frequency curve is equal to the unity gain bandwidth of the op-amp. We'll see it. Since the gain bandwidth product is constant, this is very important. Please remember always that gain and bandwidth for any op-amp circuit will be constant. If one will increase, second one will decrease, but they will maintain the constant multiplication. Okay. Since the gain bandwidth product is constant, obviously the higher the gain, the smaller the bandwidth, and vice versa. If negative feedback is used, gain decrease from A to A divided by 1 plus beta. We have seen this is the, in the block diagram, we make the block diagram and we have found the transfer function. The transfer function was A divided by 1 plus A beta. Okay, this is for closed loop. If you have open loop, so for the open loop you have only A. But once you feedback it negatively, you are getting 1 upon 1 plus A beta. So it's going to reduce by this factor. Is it okay? Initially it was A, now we are going to reduce it. Okay, that's why we are dividing by 1 plus A beta. So therefore the closed loop bandwidth increases by 1 plus A beta. Remember this point. Your gain is going to decrease by 1 plus A beta. Your bandwidth will increase by factor 1 plus A beta, and the multiplication to both of them will be constant. I hope this point is pretty clear to you. Okay friends. Now bandwidth feedback is nothing but, see, bandwidth with feedback. What will be the bandwidth with feedback? So we are multiplying the initial bandwidth or without bandwidth without feedback with A plus A beta. Why we are going to do like this? Because in the closed loop, the gain is, this is the final gain, you can say, open loop gain divided by 1 plus A beta. The gain is going to reduce by this factor. So definitely your bandwidth, new bandwidth, or I can take bandwidth for closed system, and instead of AF I can take IC, the gain of closed system. So bandwidth of closed system will be multiply by A plus A beta, or will become A plus A beta times of initial value if you will give it the name BW0. Okay friends, so this is the bandwidth. Now if we'll talk about the application of op-amp circuit, this is the figure 4 given over here. What are the application where we are using the op-amp circuits? So the first one is integrator. Integrator means if you are applying some input stage Vin at this inverting terminal. So at the output you are not getting direct connection with V1 and V0, means direct linear relationship. Here we'll get the linear relationship, but in this manner. Whatever input we are applying, it will be integrated over the period. Okay, so output is coming like this, V0 equal to minus 1 by R 0 to T V in dt. How it's coming, we can do it. Okay, but let's check the circuit. The circuit is like we are introducing capacitor in the feedback path. What we are doing, we are introducing the capacitor into the feedback path. By introducing this capacitor, this thing input will be integrated over period of time, and at the output we'll get the integration of input because of this capacitor only. So let me erase it and then we'll see. A circuit in which the output voltage waveform is the integral of the input waveform is called the integrator. Shows an integrator circuit using op-amp. So here the feedback element is capacitor. The feedback element, if feedback element is capacitor, your input will be integrated. The current drawn by op-amp is 0 and also the V2 is virtually ground. So whatever voltage will be at V1, the same voltage will become over here, and the current drawn by op-amp is always 0. Okay friends? So therefore I1 is IF. So this entire current now will go to feedback circuit, and V2 equal to V1 by virtual ground concept, and that is equal to 0 also. So what is the important? The important is for this circuit you will get V0 equal to minus R by RC, minus 1 by RC from 0 to T V in dt. Okay friends? The output voltage is directly proportional to the negative integral of the input voltage. Why it's coming negative? Because we are applying the input at inverting terminal. So whenever you apply some input to inverting terminal, definitely in the output you will get negative sign because your input will be inverted. So in the output voltage is directly proportional to the negative integral of input voltage and inversely proportional to the time constant. Because we have seen the formula, V0 is minus 1 by RC 0 to T V in dt. Is it okay? So if the input is a sine wave, let's take input is sine wave, output will be cosine wave. Output will cosine wave because the sine integration is cosine. Okay friends? If the input is square waveform, the output will be triangular waveform. I'm sorry for this. Triangular waveform you can see over here. This is the step function. If you will integrate step function, it will become ramp function. Okay. So for accurate integration, the time period of the input time t must be longer than or equal to RC. RC is our time constant of the circuit. So your t should be, for accurate integration if you want, the time period of the input signal. So this is the period, right? This period should be higher than RC. Okay. You can see in this figure shows the output of integrator for square and sinusoidal inputs. Now we'll see integration is over. Now we'll see the differentiator. Okay, so it will differentiate. What is the difference between circuit of integrator and differentiator? Differentiator, in the integrator this capacitor was in feedback path, but here it will be in this input path. We are just changing the position of capacitors only. A circuit in which the output voltage waveform, if the differentiation of input voltage is called the differentiator or differentiator, yes. Or in other words, I can say differentiator. So, in this case, again, this is the case, non-inverting terminal, V1 will be over here, V1, V2 both will be 0. So, in this case, the output you will get will be minus RC, definitely minus because the input at non-inverting terminal. So, minus RC d by dt of V in. In the integrator case, it was minus 1 by RC. Here the input dt. Integration of input, differentiation of input. So if we'll differentiate this step function, it will become unit impulse at that particular point. Is it okay? If you will differentiate this sinusoidal waveform, it will become minus cosine. Okay. Sorry, if you will do differentiation of sine waveform, sin x, sin t, it will become cos t. Okay, friends. Now, voltage to current converter. So, this is figure 3 given over here. Now, we will convert voltage into the current. See, simply over here. This is the circuit given. By virtual concept, this V in will become over here. This will be V in. If this is V in, we have I in our hand or not? I in will be V in divided by R. Here it's V in. So you converted voltage into current. Is it okay to you? See, shows a voltage to current converter in which the load resistor RL is floating or not connected to ground. This RL is not connected to ground. The input voltage is applied to the non-inverting input terminal and the feedback voltage across R, where is the R? Here. This is the feedback voltage across R, drives the inverting input terminal. Okay. So who is going to drive this? The voltage you are getting or the current you are getting by this feedback. Okay, because at the inverting terminal you are not connected directly any input. Here only you have only feedback input. But at the non-inverting terminal you applied V in. Okay, friends. So the input voltage is applied to the non-inverting input terminal and the feedback voltage across R drives the inverting input terminal. This circuit is also called a current series negative feedback. Current series negative feedback amplifier. Because the feedback voltage across R depends on the output IL, definitely. The feedback input depends on IL. Okay. And is in series with the input difference voltage VD. This is in series with the input difference voltage, definitely. So IL will be IN. Why? Because the current drawn by op-amp circuit is 0. So IL will be definitely equal to IN and will be equal to VN by V in by R. So you converted the voltage into current. Okay. Now come to this current to voltage converter. So this is the circuit diagram of current to voltage. How it's going to convert it? See, in the shown in the figure, the circuit shown in the figure is a current to voltage converter. Due to virtual ground concept, this 0 will come over here. Through R is 0 and the input current flow through RF. So if this is 0, there is no current in this, same potential difference. So this entire IN will go to this side. The current in this is IF. So IF will be equal to IN. So due to virtual ground, the current through R is 0. And the input, definitely the current in this will be 0 because this is 0 and this is 0. There will be no current, potential difference 0. And the input current flows through RF only. This entire RN will go to RF. So what will be the V output or V naught? V naught will be definitely RF into I in. Here the drop will be like plus minus and drop will be RF into I in. So this is 0. So in this circuit, if you apply KVL, you get V naught equal to minus RF into R in. Okay. So at the input stage, you applied I in and you are getting voltage. The lower limit or current measure with the circuit is set by the bias current of the inverting input. This is your voltage. This is your current. So I hope this is also clear to you. Okay. We'll take one problem and we'll bind up this session. Okay. This is the problem came in GATE 2011. And the problem given is 33K connected with 5 volt. This is 5 volt like this. This connected to BJT Q1. Let's take it Q1. And the collector of this connected with 5 volt. This is the application based equation and the application of op-amp and BJT we are using over here. This is minus, plus, over here 1 volt. Perfectly fine. This one is 100. Here V naught. And the question is, assume base emitter voltage 0.7 volt. Wait. Assume base, where is, base emitter. This is 0.7. We always consider it 0.7 VBE. Beta of this is 99. Beta is 99. The output voltage V naught in the ideal op-amp circuit shown below is asking for V naught. What is the V naught over here? Options are given. A is minus 1 volt. B is minus 1 by 3.3 volt. C is 0 volt. And D is 33 volt. Okay. So how to start it? So dear friends, by virtual ground concept we have seen this 1 volt will come over here. Now you can apply nodal analysis over here, but you don't know what is the current into this. The current is IE, definitely IE. And this is 1 volt voltage given with respect to ground only. So let me find out the current in this circuit first. Then I will apply nodal analysis over here. So I'll start with this. This is the input circuit. I have to find this IE. This IE will start from ground and will come to the ground. So we are getting 5 volt. Here I am getting minus 33K is given. 33K of IB. And IB is what? IE divided by beta plus 1 means 100. Is it okay to you? Minus 0.7. Perfectly fine. And I entered into the emitter terminal. In the emitter terminal, I got the 1 volt battery. So this is 1 equal to 0. Only one unknown IE, and that IE I want to find out. IE. Okay. So this is 5 minus 1, 4, and this is 7. 4 minus 7, so 3.3. Minus 33K, 100 also, IE equal to 0. Okay. So you will take to this side. It will become 3300 divided by 33K is equal to IE. Correct? So it will become 100 by K. So it is 0.1. Okay, so I made some mistake over here. 3.3 into 100, it will be 330 only. So it is 0.1. So this is 10 milliampere. So you got the current IE, that is 10 milliampere. And the direction of current is this. Now I can apply nodal analysis over here. The incoming current is 10 milliampere plus 1 minus V naught divided by 100. 1 minus V naught divided by 100 equal to 0. So minus 10 milliampere plus 1 by 100 minus V naught by 100 equal to 0. So this is minus 10 milliampere and this is plus 10 milliampere. So this will cancel out. So you'll remain with V naught by 100 equal to 0. So your V naught is 0 volt. So answer for this circuit will be 0 volt definitely. So friends, this is all about this session. We'll meet in the next session with new types of problems and we'll switch to the schematic trigger also. Okay. We'll meet in the next. Till then, take care and bye.